Hello, Mr. Melo here, your online math teacher, and welcome to my channel. Today we're going to be continuing my video series on confidence intervals, and in particular look at one sample t-intervals for population mean. So if you find this video helpful, consider smashing the like button, subscribing, and let's go. And also, if you notice, this is a new video format I'm trying out, so let me know what your thoughts on this are. So let's jump into this. So here's the problem we want to look at. You are a student at a large university and want to study the GPA of full-time enrolled students at your university. And as a student, you take a simple random sample of 72 other students and record their GPAs. And you find that the mean GPA of your sample was about 2.9 with a standard deviation of about 0.15. But we really want to know about the mean GPA of the entire full-time enrolled student body here. So we're going to construct a confidence interval for that. So in particular, we're interested in a 95% confidence interval to estimate our sample or our population mean. So to do that, we want to know how can we structure our work and what do we need to do. So we're going to follow the state, plan, do, and conclude process. So in stating, you're going to let us know what parameter are we looking for and what confidence level do we want. In plan, you're going to identify the inference method we're using as well as check any conditions we need. In do, you're going to actually do your calculations, where this is where you're going to actually find the interval. So this is where most of the work comes in. And then finally conclude, that's interpret our confidence interval. So let's take a look at the state phase of this. If we want to state the parameter we're interested in, here we want to know what is the true mean GPA of full-time enrolled students at this large university. That's what we want to find. And the confidence level we want here is 95%. That might be different depending on the problem you're looking at. It's only going to change the critical value later on in the problem, so it's not a huge deal yet. So this is all the state phases. Identify your parameter and what is your confidence level. From here, you move to the plan phase. So you need to plan what inference method are we using. In this case, one sample t-interval for population mean, as well as check the conditions that are appropriate here. Because we're interested in our population mean, and we're looking at a sample statistic, what we're going to lean heavily on is our knowledge of sampling distributions. So what you can think about when we're finding these confidence intervals, you're really looking at a sampling distribution. In this case, the sampling distribution for our sample means. So we need to check the conditions for that. But beyond that, we also want to know a randomness condition. Are things random? In this case, yes. We took a simple random sample of 72 students from our population. But the reason for this randomness is because you need randomness to make inferences about your population. So to be able to generalize what we see in our sample to a greater population, so we need to add this in. After this, we're really looking, do we have the appropriate conditions so we know what our sampling distribution looks like? And those conditions are the 10% condition. We're sampling without replacement here, so we need to make sure our samples aren't too big. In this case, they're not. 72 is definitely less than or equal to 10% of the entire population of interest. And like I said, this allows simple random sampling to be fine, and it allows you to know what your standard deviation formula is for your sampling distribution for sample means. In this case, we're going to actually call it standard error because that, and we'll see why in a second, but this is good for us. But we also need to know the shape. We want to make sure, is the sampling distribution for sample means normal? Because when things are normal, we have lots of tools, but if they're not, we struggle at times. And in this case, it is. We know that our sample size is big enough. 72 is bigger than or equal to 30, and our sample standard deviation is finite, so we can apply the central limit theorem here to tell us, hey, well, we maybe don't know what the population distribution shape is. The sampling distribution shape, that is normal. Central limit theorem is good. So even though central limit theorem tells us that's normal, we actually are going to be looking at a t-distribution to construct our interval, and that's because in that formula for standard deviation for our sampling distribution, you need to know the population standard deviation, and we don't know that here. We have to estimate that with our sample standard deviation, and because of that, it's going to add in additional variability. So if we use our z tables and use a normal distribution, we'd actually underestimate or overestimate our confidence level here. If we want 95% confidence, maybe it would be a few percentage points less than that. So we need a t-interval here. Basically, t-intervals help make up for the fact that we're approximating our standard deviation. That's why we're calling it standard error also. So now we can go to do. So what do we want to do? We want to compute our confidence interval. So where should we start? Well, we know our point estimate is going to be our sample mean of 2.9, and we can compute our standard error using the standard deviation formula for our sampling distributions. But because we don't know the population standard deviation, we use our sample standard deviation of 0.15, then divide by the square root of our sample size of 72. We get a standard error of 0.018. Again, this is really just your standard deviation formula. We just call it something different. So this is standard error. So now what we're looking at is a t-distribution, which looks kind of like a shorter, fatter normal curve, where we want 95% of our data in the middle, and we want these tails outside of the endpoints of our confidence interval to each have 2.5% in them, because we want 95% confidence. And we know A or B are equal distances away from our point estimate, because we need to find the margin of error, which is that distance. But this picture's hard. We don't have a table for this, but we do have a t-distribution table. So we take this over and we transport it into t-distribution land. So we have a picture as follows. We want the t-distribution where our critical value t star, if we take positive or negative that value, 95% of the data will be between those two numbers, and just 2.5% will be in each of those tails. So the degrees of freedom in this case, because you need that for your t-distribution, is going to be 71. The reason it's 71 is it's one less than your sample size for these types of problems. So we have a t-distribution with 71 degrees of freedom. So now we can go find our critical value t star. To do that, you'll probably use either technology or a table. I'm going to use a table. And when I look at my table, it usually has an illustration of what areas your table gives you. So here we see that the shaded area is that right tail. So since we want 2.5% in that right tail here, and we want a 95% confidence interval, when I looked at my table, I go over to the column that corresponds to 2.5%, so 0.025, and I go to, and you'll also see that that's 95% confidence level. It says 95 at the bottom too. But also, I go to the row for the appropriate degrees of freedom. Now, I have 71 degrees of freedom here, and that's not an option in the table. A lot of the time, you'll run into this issue. So when you do, choose the first degrees of freedom option that's less than what you want if your degrees of freedom isn't there. So 60 is the next number below 71 in our table. So I'll go to the 60 degrees of freedom row. And when my row and column intersect at 2.000, that tells me that this critical value t star that I want is going to be 2.000 here. So you might need not have your degrees of freedom you want in the table. Just go to the next one less than it if it's not there. And we get our critical value here. So we have a critical value. We have a standard error. That means we can now find our margin of error. That's going to help us jump from our standardized picture back to our actual picture we're interested in, our actual scenario. So to find that to use the critical value and standard error to find our margin of error, we just need to multiply them. So I multiply my critical value and the standard error, and that's going to give me a margin of error of 0.036. Now that you have a margin of error, you know how far away A and B are each from our point estimate. B is going to add the margin of error to our point estimate. A is going to be what we get when we subtract our margin of error from our point estimate. And we can do both of those out to get a lower bound for our confidence interval of 2.864 and the upper bound of 2.936. So this gives us our 95% confidence interval. So we have the interval now. After this, though, we then need to go and actually interpret our confidence interval. In that case, that's our conclusion phase. So we are 95% confident that the interval from 2.864 to 2.936 captures the true mean GPA of full-time enrolled students at this large university. So that is the last step here. Now, you're not writing it in a PowerPoint like I have. You're probably going to write it up by hand. So your by hand solution should probably look something similar to what I have here. I still have everything we just talked about in the state plan, do and conclude process, but it's just in writing form. So that is it. I hope you found this video helpful. If you did, consider smashing that like button, subscribing, and have an awesome day.